Hi, my name is Elle Priesing, and in this video, we are going to be comparing the vapor pressure of two solutions and prove which one would be a better deicer. So this statement, or the question, is a solution made by dissolving 25 grams of ethanol in 100 grams of water has a higher vapor pressure than a solution made by dissolving 25 grams of potassium chloride in 100 grams of water, but the salt solution is a better deicer for a sidewalk than the ethanol solution described. So what we're first going to do is we're going to take a look at solution 1 and what we are given. We know that we have 25 grams of ethanol dissolved in 100 grams of water. So our second step is to first convert the grams of ethanol into the moles of ethanol that we have by using the molar mass. Then we're going to do the same thing for water and convert 100 grams of water into 5.549 moles of water. Our second step is to do the mole fraction for each compound. To find the mole fraction, we do the moles of solute over the moles of solute plus the moles of solvent. And for this solution, to find the mole fraction of ethanol, we put the moles of ethanol in the numerator over the total moles. And here we get 0.0906. And remember that the mole fraction is unitless. Now that we have our mole fraction for ethanol, we're going to do the same thing for water. And we get 0.9109. Our next step is going to be to calculate the total vapor pressure of this solution by using this equation. So we calculated the mole fractions above, and now we know that the pure vapor pressure of ethanol is 58.7 torr, and that the pure vapor pressure of water is 23.3 torr. So to solve that out, we get the total vapor pressure of this first solution to be 26.5 torr. Now we go on to our second solution. In our second solution, we know that we are given 25 grams of KCl, or potassium chloride, and 100 grams of water. So just like we did for the first solution, we're going to convert 25 grams of KCl by using the molar mass and converting it to moles of KCl. And here we get 0.3353 moles. Do the same steps as before with water to get 5.549 moles of water. Now we're going to calculate the mole fraction by having the moles of KCl in the numerator over the total moles of the solution, and we get the mole fraction of KCl to be 0.05698. Now, since KCl is a solid, it does not have a pure vapor pressure. So we're going to use this equation here, change in pressure equals the mole fraction of the solute times the pure vapor pressure of the solvent. Now KCl is a non-volatile solute in H2O, so again, this is why we are using this equation. Our next step is to plug in our values that we have gotten above, and we get 0.05698 times 23.3 torr, because that is the pure vapor pressure of water, and we now get that our change in pressure is 1.328 torr. So since that is only our change in vapor pressure, we must add that change to the normal vapor pressure of pure water at standard conditions. So then we get that the total pressure of KCl is 24.6 torr. Now if we compare this value to our previous value of 26.5 torr, it is clear that the vapor pressure of the first solution, ethanol, is higher than the total vapor pressure of our second solution, KCl. But to prove that this salt solution here, KCl, is a better deicer for a sidewalk than the ethanol solution described, we must now take a look at the change in the freezing point depression. So this formula is the Van Hoff factor times the freezing point depression constant multiplied by the molality of the solute in the solution. So we can first do this with ethanol. But before we plug in the numbers into the equation, we must calculate the molality of ethanol, which is moles of the solute over the moles of the solvent. And here we get 5.426 molality. Now that we have our values, the Van Hoff factor is 1 multiplied by the freezing point depression constant of water, which we are given, multiplied by our molality that we just calculated. We get that the freezing point depression of ethanol is 10.1 degrees Celsius. We must do this now for KCl in order to compare them. So we calculate that the molality in moles over kilograms gives you 3.553 molality. Plug it in again to the Van Hoff factor multiplied by the freezing point depression constant of water, 1.86, times 3.55 molality gives us 13.2 degrees Celsius. Now we must remember that these units cancel out and leave us with degrees Celsius. Our next step is to realize that the 25 grams of KCl lowers the freezing point depression more than the 25 grams of ethanol. This is because there is a larger change in KCl, 13.2 degrees Celsius, as compared to a smaller change that ethanol will create, 10.1 degrees Celsius. Therefore, KCl is the better deicer.